Alrighty then, here we are for podcast 2.2. Let's get right to it. This time we are talking about the basic types of chemical reactions. So we can look at a combination reaction first. Combination has the same type as what we know, synthesis, and sometimes they call this composition reactions, like the opposite of decomposition. So all of these refer to putting things together. And I'll show you an example of what we would mean by a combination reaction. When could we put two things together? Suppose we took magnesium, the element, and combined it with oxygen from the atmosphere, and we made that white powdery magnesium oxide. Then that would be an example of a combination reaction. Typically what you'll see is single elements on the left and one product by itself on the right. When you have only one product, then you know it's a combination reaction. Decomposition is the opposite of combination, where we take a compound and break it apart into what it's made of. So calcium carbonate is made from metal calcium oxide and carbon dioxide. Now I chose this one on purpose because I do expect you to memorize the carbonate decomposition. And then from there you'll be able to surmise other decomposition reactions. So we always get the metal oxide and carbon dioxide here. Let me show you another example and why this is so useful to know. We have metal oxide and carbon dioxide, but what if we had like calcium sulfate? Then you would get the metal oxide and the sulfur trioxide. See, we just took one of the oxygens and put it here, and then write what's left right here. So the decomposition of basically any substance you can predict by following the simple rule of the calcium carbonates. Remember, metal oxide and carbon dioxide. So use that to help you out when you see other types of equations. Now let's look at single replacement. In a single replacement reaction, you would have an element all by itself reacting with a compound. And it's going to try to kick out a similar element. So cations can replace cations, and anions can only replace anions. We wouldn't be able to replace a positive charge with a negative charge because then we'd have two nonmetals together, and that just won't work. Alright, so that's an example of single replacement. Let's clear this out. There we go. We also have double replacement where two compounds react and they would be trading partners. Carbonate ditches the potassium and goes to hang out with barium instead, and the chloride goes to be the dancing partner with the potassium. So that's how double replacement works. And then combustion is where we would combine things with oxygen to release a lot of heat and light and energy. So we typically are looking here for combustion at hydrocarbons, right? A carbon, a hydrogen, and sometimes other things too, but that's our backbone for a hydrocarbon. That's it. That's the 5 basic types. We're going to focus on the types of reactions that are not typically redox reactions, where redox is not our focus, but let me show you how to predict products for basic reactions. So let's start with double replacement. Here's one sign that a reaction has taken place, that a precipitate forms. So what you're looking for here is two ionic compounds. If you have two ionic compounds reacting, meaning you've got a metal here and a metal here, then those are ionic compounds. You're probably going to have a precipitate forming. So we'll look at our solubility rules and see what we think might happen between these two. Oh, go back. So let's make a prediction. Cadmium is Cd, and nitrate is NO3. Let's crisscross those charges, two of these and one of those, and it's going to react with sodium sulfide, Na2S. What could we predict to form? Well, remember the Nockel-No-So rules? Anything with sodium and nitrate is going to be soluble always. So we know that's going to split apart. That makes these guys spectator ions. So we would put these together, but they won't actually stick. They all stay dissolved. Now I ran out of room over here. let me put my other compound. When I switch these two, I'm going to put cadmium and sulfur together, CdS. And sulfides are almost always insoluble. So that's our precipitate right there. Now let's double check to make sure we can balance everything. I need to have 2 sodium ions and 2 nitrate ions, and life is good. Everything's balanced. Alright, so that's how we would write the balanced equation for a double replacement reaction where precipitate forms. Use your solubility rules. Let's look at a different type of reaction. Acid-base. These have keywords that would say something like equimolar. That means the concentration is the same. And diprotic. If you see the word diprotic, then you know you're dealing with an acid here. So, what do? First of all, you need to remember that nonmetal oxides react with water to form acids every single time. So if you have sulfur dioxide or sulfur trioxide in water, it's going to make an acid. So let's predict. Sulfur dioxide looks like this. When we combine it with water, then how many oxygens do we have altogether? 1 here and 2 here. So guess what kind of acid we're going to make? Sulfurous with 3 oxygens. If you have sulfur trioxide, SO3, plus H2O, now count up your oxygens, and it looks like we've got 4 now. So this is sulfuric acid. So that's how we would predict the formation of an acid from a nonmetal oxide. Oh, I got another one to do. Carbon dioxide in water. It's going to look like this. CO2 plus H2O. And then count up your oxygens. H2, CO3, carbonic acid. You probably were predicting that already. Okay, what if we have a metal oxide? So it's still an acid-base reaction, but we need to see that a metal oxide in water will form a base. So let's write down what this one would do. Solid potassium oxide would be K2O, and we put it in water, and we're going to make potassium hydroxide, and what do we have left? Just 2 potassium hydroxides. That's all we gotta do. And bubbles of hydrogen gas, probably. So keep track of these. These here are combination reactions because we made an acid and we made a base. And this one was single replacement at the same time. But they'll go into acid-base reactions if we were to mix our acid and our base together. And that would make it double replacement. So I kind of have things a little bit out of order. That's okay. You guys are very clever. Alright, so double replacement is never, ever a redox reaction. They're just trading ions around. But redox reactions can be any of the rest of the types. So let's look at single replacement reactions. Here we have to use the activity series to predict the products. Here's an example. Silver nitrate is spilled on a sheet of polished copper. So then what would happen here? I guess I don't need parentheses because silver nitrate is AgNO3 and it's spilled on a sheet of polished copper. We need to know, is copper active enough to replace the silver in silver nitrate? And in fact, you already witnessed this reaction in a demonstration in your general chemistry class, and hopefully again in AP chemistry by now. So we know copper will indeed replace the nitrate. How do you know which kind of copper to use? Well, to be quite honest, it doesn't matter as long as you balance the equation. So in this case, I made cuprous nitrate. Suppose you had predicted the formation of cupric nitrate instead. So then what? Then we have to have 2 nitrates because the copper would be a 2+ charge. And that means you're going to have to come back here and balance the equation. 2 of these, and then balance the silver. So it doesn't really matter which one of these 2 you predict as long as you balance the rest of the equation so that it's consistent with the product that you chose. Either way you do it, works for me. Now there are certain conditions that will tell us which is more likely to form, but I'll show you that later. Hot chlorine gas is passed over solid iron 3 bromide. Here's another type of single replacement reaction, but in this case it's the nonmetal, so it cannot replace the iron. It's going to try and replace the bromide. So hot chlorine gas has this chemical formula, Cl2, and it's a gas, and it's passed over iron 3 bromide. So since the iron has a 3+ charge, then in the product I'm going to predict that it would keep the 3+ charge. There's no reason to suspect that it would do anything different. And then bromine is a Brinkelhoff element, so now we have to balance this appropriately. Make sure everything works for diatomics. There we go. So that's how we predict single replacement reactions. In nonmetals, it goes from top to bottom. Chlorine is more active than bromine, but fluorine is more active than chlorine. So look at the periodic table. Yeah, top to bottom, referring to the periodic table. But for metals, I'll show you how to use your reduction table to predict activity. You don't have to memorize the activity series, but for now, it's not a bad idea to generally know what things tend to not be very reactive, like silver and gold, for instance. Okay, let's look at another type of redox reaction. Decomposition reactions. I talked to you about the carbonate rule. Do you remember what it was? What happens when calcium carbonate is heated? Let me write this out. CaCO3. We got to put a triangle up above our arrow, and we make the metal oxide and carbon dioxide. Fabulous. Oh wait, I got to balance. It is balanced. That's lovely. How about sodium sulfate? Let's follow the same rule. Sodium, Na2, sulfate, SO4, is heated. All right, put a little triangle. And so now we're going to make the metal oxide, Na2O, and then what's left? SO lost one of its oxygens, so it's SO3. Sodium oxide and sulfur trioxide will be your products, and it's already balanced. So that's how we do decomposition reactions. How about a synthesis reaction? How do we put two things together? Usually we get just one product, and I think we just did this, right? Chlorine gas is passed over iron filings. Now this is a little bit different from the last one. Chlorine gas passes over pure iron filings. Alright, now what do you want to do? You want to call it iron 2 or iron 3? Frankly, I don't care what you do. Either one will work, as long as now you balance it, and that's why I picked iron 2, because hey, it's balanced. Is that cheating? No, no, no. It's being smart. Sulfur in standard state is S8, and it's burned in air. So what would we predict for this product? Well, I would predict S and O to come together. So what could I make? I could make SO2 gas, I could make SO3 gas, but I probably won't make SO4 gas because that SO4 makes a polyatomic ion. So either one of these, and then we balance the charges, or the atoms, sorry. So I need 8 sulfurs, and that gives me 16 oxygens, so I put an 8 there. What if it was this one? S8 plus O2 makes SO3. Alright, no big deal, I can do this. I need 8 sulfurs, and that gives me 24. So put a 12 there, and we're all balanced. That's it. Great. Let's talk about a different kind of combination reaction that you have never seen before. Coordination compounds form when transition metals react with excess concentrated ligands. So you'll look for these clues. You need to have a transition metal, and often aluminum gets involved. Even though it's not a transition metal, it's pretty close. And then excess concentrated is a clue that you're going to have a ligand. These are your ligands that we tend to work with. Water, and then maybe chloride, hydroxide, and ammonia. These are common ligands in complex ion formations. So all you do is take the charge of your metal and multiply by 2, and that will tell you how many ligands to attach to it. Then what do we do? Balance the equation by mass and by charge. You've never seen this before, so I'm going to do 2 examples of these. Iron, ferric ions. So okay, so what kind of ions are the ick? That's a higher charge. So Fe3. Ions are placed in concentrated potassium thiocyanate. Potassium is a spectator ion. That's going to fall away. So we have thiocyanate is this ion here, and it has a -1 charge. Good. Now take the ligand number. What should we put here? How many? Double the charge. So 2 times 3 is 6. We're going to attach 6 thiocyanate ions to our iron 3. And so I get SCN with a 6. Okay, now let's predict the charge. I have 6 negatives and I have 3 positives, so the charge of this overall ion is a 3-. It forms a complex where they all stick together and all carry a charge. Now suppose that you forgot to do the charge thing and you only put 1 thiocyanate ion with your iron. Then what? Then you would get FeSCN, and then look at the charges. I have a 3+ and a 1- gives this complex a 2+ overall charge. So what if you did that instead? So what? It still works. You still followed the rules because it balances the charge and balances by mass. So you don't have to exactly predict the right products because this may be a product that forms and this may be a product that forms, and they're both correct. So when you have competing reactions, who's to say this won't happen? It just might, but this one might happen too. So you can get credit on my tests and on your AP Chemistry exam if you predict products that make sense and then you balance the charge and balance the atoms, balance by mass, and balance the electrons. So remember, you don't have to be perfect, you just have to be good. Oh dear, what did I do? Go back. There we are. Let's do another example. Let's look at zinc nitrate. And it's not called zinc 2 nitrate because there's only one kind of zinc, and it's the 2+ kind. What do we do with the nitrate? Don't worry about that guy because nobody wants to hang out with nitrate. It's a spectator. And it's added to concentrated, here's our keyword, concentrated ammonia to form tetraamine zinc 2. Well, I gave you a big fat clue here. Here's my ammonia, and how many of those do I want? This says tetra, 4. See why? Double the charge, that's how many ligands we're going to attach. Alright, so I have zinc with 4 ammonias, and that's what makes it tetraamine, and then the overall charge is going to come from the zinc. The zinc has a +2. Ammonia is a molecule with 0 charge, so it contributes nothing at all to the charge. So the whole thing is a 2+ charge. That's why in the name it says tetraamine zinc 2. So pay attention to the kinds of ligands you have and the charges that you have, and you'll be able to balance these with no trouble at all. But we're going to practice so that you get really good at this. Alrighty then, what's next? Balancing. Hey, let's do this. If I could clear my old writing, that would be lovely. There we go. So now we have 2 ionic compounds, and it's an acid-base reaction, so I'm forming a molecular substance here, water. That's not going to go away. And then this precipitate calcium phosphate. Alright, what are we going to do with this bad boy? How do we balance this? Let's use a table. For calcium, I have 1 here and 3 here. And for hydroxide, that stays together, and I'll show, whoops, hydroxide. I'll show you how right here. I'm going to change this to HOH so you can see where our hydroxide is. That means we have 1 hydroxide here and 2 hydroxides on this side. Hydrogen ions, I've got 3 in the acid, and then only 2 here in the water. No, I have 1, HOH, right? And now phosphate stays together, so I can count it as all one thing. I have 1 here and 2 there. So what should we fix first? I vote for calcium. Let's do this. I need to have 3. So multiply this side by 3. That was for the calcium, but that also affected my hydroxide. So now I have 6 of those. So I've got to come across to this other side and balance hydroxides. I want to get 6, so I need to multiply 1 by 6. And when I changed hydroxide, that affected the hydrogen in my water. So that got multiplied by 6. Now we go back to the other side. How do I get to 6 here? Multiply by 2, of course. So I need 2 of these. That automatically changed my phosphate, but that's good because it made that work. So that's how we use the table method to balance. And I have 3, 2, 6, and 1. Great. Let's do another one. Chromium metal, Cr, is placed in a container of sulfur gas. Alright, so it just says sulfur gas. That means it's in elemental form. It's not combined with any other atoms, right? So I would predict here when 2 elements react, it's typically going to be a combination reaction. Identify the type of reaction you have, and that will make it easier to predict the products. So what would happen here? Cr, I think we have 2 plus or 3 plus for those charges. I'm going to give it a 2 plus, and sulfur is a 2 minus. So now let's balance this, and we're all set. What if you used chromium 3? No big deal, just balance it when you're done. Alright, let's do another one. What type of reaction do you think this one would be? We started with one product alone and ended up with more than one thing, so that's got to be decomposition, right? And we already have the formulas, so we just make a table. Potassium, chlorine, and oxygen. 1, 1, and 1 of these and 1 of these, 3 of these and 2 of these. So we can see where the problem is. I need to have 3 oxygens. That only changed the oxygen. So now let's come back over here and get 6. Multiply oxygen by 2. And now I messed up my potassium and my chlorine. So I got to go back on the other side and fix it. Multiply these both by 2 by putting a 2 right in front. You probably could have balanced this one by inspection, but I used the table just to be thorough and help you step it through. Okay, here's another one. Let's change the words into formulas here. Iron 3 sulfide. So iron with a 3 charge, and sulfide always has a 2 charge, so that's this bad boy. Reacts with gaseous hydrogen chloride, so not hydrochloric acid, but HCl gas, to form solid iron 3 chloride. That would look like this. And then hydrogen sulfide gas would be H2S. And this is a solid. Alright, so we've got all this stuff going on, but as long as you can write the formulas correctly, then you'll be able to balance it correctly. So let's get our formulas down. HCl gas. And then we're going to make iron 3 chloride and hydrogen sulfide. Alright, since none of these are aqueous, then none of them would be considered spectator ions, right? We just have to start balancing. So let's start here. I need 2 irons, and I'm going to have 6 of these. That works because I need 3 sulfurs, and that gives me 6 hydrogens. So there we've balanced our equation by inspection, and it worked. Yeah, you like how I picked the hard one to do by inspection, huh? Oh wow. Let's do one more. I think this is our last one for today. This one looks like single replacement, so we have to know, is there going to be a reaction? Is aluminum going to be more active than iron? So we check our activity series and see that aluminum can replace the iron, so we actually get a reaction that occurs. And we predicted it already. So let's see. Let's just clear out this writing so I can put my coefficients in. I need 2 irons. There we are. And then how many aluminums? 2. And then oxygen is 3. There we go. Done. Oh, I said we might have our last one, but I was wrong. Excess concentrated. There's that key word. Potassium hydroxide. Potassium is a spectator. That's going nowhere. And we're adding it to a precipitate of zinc hydroxide. Alright, so we have zinc hydroxide already. We're going to add more hydroxide to it. So we're going to get one of those coordination complexes. Alright, what do we need to do? I say let's just add it. Okay, so we get zinc hydroxide, only now it's trihydroxide. And let's look at the charge. This was a 0, and we added a minus, and so it's a -1. So that would work. Suppose that you wanted to double the charge. Alright, so then we would end up with 4 hydroxides for our product. And then we would have a -2 instead of the -1. No big deal, just balance it. If you're going to add another hydroxide, then make sure it's balanced by mass. Mass and charge both have to be balanced. Either of these answers is equally right, and so you get credit for both. That's it for balancing equations and identifying the type. So, I'll see you next time.